Okay, let's start actually chapter 4. We're only going to do two sections of chapter 4, 4.1 and 4.3. I really would like to do quite a bit more. This is, to me, the most important part of mathematics many people will study, and I actually wish that we had more emphasis on what is known as linear algebra, because I think it needs to be emphasized just as much as calculus, if not more these days. It has a million computer applications, and for those people who like video games that have high resolution and run smoothly, for people who like Disney or Pixar type animated movies, you can think progress in linear algebra, of which you're getting a very, very small preview of right now, but you can think the progress and the speed to those computer graphic renderings to linear algebra techniques. So let's just start. So what I've done is I've drawn a Cartesian plane. Here's my y-axis, and here's my x-axis. And then I've drawn a line in yellow, and we just know it's a line. So from what we learned before, we know it has the equation in the form ax plus by equals to c, where not both a and b are equal to 0. And that's going to be line 1. And here's line 2, and we're going to call it nx plus my is equal to r, because clearly it has different coefficients for the x term and the y term, because it's a completely different equation, or the graph of the line is completely different. So it has to have a completely different equation. So let's examine a point right there. Now we have that point right there as the value x1 and y1. And since x1 and y1 lies on the graph of line 1, that means when I plug in the value of x1 into this equation and y1 into this equation, I get a true equation. Let's come over here to the purple line. We'll put a little point on the purple line. I'll call that x2, y2. It's a different point. And since the point lies on line 2, I know when I plug in my x2 in for x up here and my y2 in for y up here, I'm going to get a true equation. Now we can't actually do that because I don't know what the value of n is, and I don't know what the value of m is, and I don't know what the value of r is. I just want to talk about general lines, not specific ones. And down here I actually pose a question. We want to know if there exists at least one, maybe more, ordered pair solution or solutions, x comma y, that makes both equation 1, ax plus by equals c, and equation 2, nx plus my equal r, true. We'll see if we can graphically figure that out. Do these two lines share a point? Well, if I look at this point right here, and we'll call it x3 and y3, then x3, y3 lies on both the purple line. So when I plug in x3 and y3 into this equation, it's a true equation. But it also lies on the yellow line. So when I plug in x3 and y3 up here to equation 1, or down here is where equation 1, they're the same, I'm going to get a true solution. So visually, we can see that depending on the lines, that it is sometimes possible to find an x and a y, which is an ordered pair, that make two equations true. So think about, this is a really, really good example of when that happens. Think about when it may not happen, or when there's an infinite number of solutions when there's no solutions or there's one. So we're actually going to be talking about, so I'm just going to give you some possibilities to think of. So we just actually visually discovered one. One possibility, there is exactly one ordered pair solution. And when I say solution, I mean a solution to both equations. So we're literally looking at two equations simultaneously. And what are those equations? Well, right here are equation 1 and equation 2. They're not really equations, they're equation forms, because we don't know what A is, we don't know what B is, and we don't know what C is. So there's no way we could possibly evaluate them, but that's what I'm talking about. Two different equations. You'll see plenty of two different equations later on. So that's one possibility. Another possibility, and we have that visual solution, don't we? This visual example right now, which is literally one in an infinite number of possibilities, there is only one point that lies on both lines, and that's the only point that makes line 2 equation true and line 1 equation true. So another possibility I want you to consider is the possibility that no ordered pair exists that make both equations true. And I invite you now to visually think about what that may be like. And then the third, so here is exactly one, none, and what is our only other possibility? More than one, but in this case I'm going to expand it, and infinite is clearly number of ordered pairs. So logically, the next possibility is just more than one, and they're all satisfied. But I changed it to more than one to an infinite number, because those are going to turn out to be the only three possibilities we have to deal with. So let's actually look at a particular example. Okay, let's do example 2. So we have a system of linear equations. This first, x plus y is equal to 2, we can call that equation 1, and 3x minus y is equal to minus 2, we can call that equation number 2. So the normal way to deal with this is we have to plot both of these, and you can plot it any way you want. And what we'll do, let me make my little thing a little bit smaller. We have x plus y is equal to 2, and we'll just do a table of values. We're going to divide. We have to actually do this for two different ones. 3x, two different equations. 3x minus y is equal to minus 2. So I think the table of values is the easiest way to go for each one of these. And in particular, notice that in each one of these equations, and recall they're in the general form, each one has a non-zero constant. Since it has a non-zero constant, the best way to do, I think, you don't have to do it this way, is to choose kitty corner zeros. So remember again, that means I'm choosing x to be equal to 0 in the first row. So I plug in 0 for x and solve for y. And in the second row, I'm choosing y is equal to 0. So I plug in 0 for y and choose and solve for x. And in this case, it's really easy to see x plus y is equal to 2. Well, when I plug in 0 for x, 0 plus y is 0, so that gives me y is equal to 2. And when I do the same thing, and I plug in 0 for y, x plus 0 is just x, so this gives me x is equal to 2. So right there are my 2 points. Remember 0, when 0 is in the first coordinate, that's your y-intercept. So that's the point right there. X is equal to 0 and y is equal to 2. And when 0 is in the second coordinate, it's your x-intercept. So there we go for that. So let's go ahead and draw a line through these 2 points. And remember, we're trying to solve a linear system by graphing. So coming over here to this next one, we have a different equation. Oh, yeah, I'm on the wrong color. 3x minus y is equal to 2. And again, our constant is non-zero, it's 2. So we're going to go ahead and use the kitty corner zeros here as well. So the first one says plug 0 into x. So when I plug 0 into here for the x value, the 3 times x vanishes. I get minus y is equal to minus 2. So I multiply both sides through by minus 1. That gives me y is equal to 2. Now if you're really on the ball, you already know something. You already know that there is at least one ordered pair solution for these 2 lines. Let's go ahead and do the next one, and we'll see that visually. So here I have a point 0, 2, and then point 2, 0. And over here I have 0, 2, and I don't know what this is going to be down here, but it's going to be 0 in the y slot. But I already know that at least there's one point that solves both of them, and that's going to be the point 0, 2. But let's go ahead and plug in 0 for y. So I get 3x is equal to minus 2, because y is 0, so 3x minus 0 is equal to 3x, so I get 3x is equal to minus 2, and that gives me x is equal to minus 2/3. So minus 2/3. And the point is minus 2/3. So again, let's choose maybe a slightly different color. I have the common point already. 0, 2 is a common point, and down this is 0. This is minus 2/3 and 0. So the 1 is about right halfway in between the minus 2 and 0, and then the minus 2/3 is going to be, so I'm going to say that's 1 right there, and the minus, and that's going to be 1/2, and the minus 2/3 is going to be about right there. I mean, it's kind of ballpark guessing. It doesn't really matter, but we will draw a line through both of them. Whoops, trying to freehand it, and that's never going to go over well. And draw going through this way. So there are my 2 lines, and you can see the common point, it's not drawn perfect, is there is one single solution, and that single solution is this point right here, 0, 2. So the point 0, 2 is a solution to both of these linear equations. So let me introduce now some really important vocabulary. You'll be asked questions on this on the exam, I'm quite sure. So a system of linear equations is a set of 2 or more linear equations. And what makes a linear equation, an equation linear? All of the variables are degree 1 variables. That means they don't have any exponents. No fractional exponents, nothing. And for this particular class, they're all going to be linear equations in the variable xy. So ax plus by is equal to c, where not both a and b are 0. So a solution to the set of linear equation, our set is only going to contain 2, is a set of ordered pairs each one of which makes each equation true. So if you think about it, a solution to the set of linear equations is a relation, because a set of ordered pairs is a relation. But they don't use that vocabulary here. I don't really know why not, because it's a good way to remind yourself that a set of ordered pairs is a relation. But that's not the point here. The point is to understand what a solution is. You have a set of ordered pairs. Each ordered pair is a solution to both or all of the equations in the system. A system of linear equations is said to be, and here's the defined word, consistent if there is at least one ordered pair that makes all of the equations true. For our case, all of the equations will just be two equations. A system of linear equations is said to be inconsistent if there are no ordered pairs that make every equation true. So in our case, let me bring up, I'm just going to give you some information rather than try to derive it. So for our case, and it's the case in general, if we have a system, a system of linear equations, and of two, we're always going to be dealing with two linear equations in this course. But if you want to know how games, I've never played a modern video game in my entire life. I've never ever even touched an Xbox or whatever else they have. But if you're playing those, you want to know how come their graphics are so smooth, and you're saying, oh, it's the graphics card. Well, that's part of the equation. I don't care how fast your processor is, and I don't care how great your graphic system is, if it were not for mathematical techniques to solve systems of thousands of linear equations very rapidly, it doesn't matter. It would still take 10 minutes to generate each frame. So if you like Pixar, Disney animation, video gaming, so much stuff, or if you've got kids that like those, what is it, my nephew loves Coco something or another on YouTube, all of that is made possible not only by modern techniques of computation, good algorithm for computation, the hardware that makes those computations go faster, and the underlying mathematics in the form of linear algebra that literally makes all of this doable. So here we have our system of two linear equations. There's three possibilities. It will have exactly one ordered pair solution. So when we talk about a solution, and we're talking in the context of linear equations, the solutions are always ordered pairs. So I'm going to drop that word a lot from now on because it's understood in the context. I'm talking about a system, so I'm not talking about a single value x that solves it, or a single value y that solves it, but a pair of those values in order, x comma y. Or it will have no solutions whatsoever. And or the final is it will have an infinite number of solutions. And I apologize if I am repeating myself. I tried to finish this video last night and it had been a long day and I was making mistakes, so I just cut it off. So I went back and I'm redoing a section of it. So infinite number of solutions. Now logically, for those of you who love logic, you might understand that one ordered pair of solutions, no solutions, the real third option is more than one. So it's either exactly one, none, or more than one. But in this case, the more than one is always going to be an infinite number. So I'm actually adding a little bit more knowledge to this third option than logic itself dictates. And that's just part of the mathematics that I hope you will be able to grasp actually here in just a little bit. So these two options right here consist of consistent systems. Remember, systems is, and for our case, they're exactly two for our case, linear equations. This case right here, the third case, they are inconsistent. Okay, so back to what we were doing. So consistent and inconsistent is another classification scheme for a system of linear equations. Given a system of this is another classification scheme. It's like you can classify animals different ways, right? You can classify animals as those that are domesticated and those that are not domesticated. You can classify animals as mammals and those that are not mammals. You can classify animals as those which have wings and those which do not have wings. So it should not surprise you that we have more than one classification of mathematical objects. And consistent and inconsistent is one type of description of those systems. So given a system of linear equations, an individual equation, so we're talking about an individual equation, so the system contains two, so we're talking about one of those equations, is said to be independent if it cannot be algebraically derived from the others. This means its graph is different, so visually, I just want you to think visually now here. This means its graph is different than the graphs of the other equations. So if you look at one linear equation and you graph it, and then you look at the other and you graph it, and they're two different lines, then those individual equations are independent. On the other hand, equations are called dependent if they can be derived algebraically from other equations, and we've been doing that quite a bit. You may not realize it. And visually, that means they have the exact same graph. So let me give you an instance of a dependent equation. So this is going to be equation 1. I'm going to have 1/3 x minus 5/7 y is equal to minus 1. So that's equation 1. And I'm going to produce an equation 2 that is algebraically derived from this one. The first thing I'm going to do is I'm going to notice that the LCD of 3 and 7 is equal to 21. So I'm literally going to multiply both sides of this equation by 21. And that's going to give me 21 divided by 3 is 7. 7 times 1x is 7x. That's not the color I want. That's 7x. 21 divided by 7 is 3, and 3 times minus 5 is minus 15y. So 3 times minus 5y is minus 15y, and that's equal to minus 21. So literally I derived equation 2 algebraically from equation 1. So equation 2 and equation 1 are dependent. And that's something I want you to recall, because I would much rather work with equation 2 than equation 1. And equation 2 was derived by clearing the denominators of equation 1, so its graph is identical to that of equation 1. Now if I were to just sit down, if I were to be given, ignore the stuff in blue here, that multiplying both sides of 21, if I were to be given equation 1 and equation 2, just looking at it, I might actually think they are two equations of two different lines. But as it turns out, if we went to plot them, we would quickly discover they're not. So that's the second conceptual classification scheme, talking about individual equations. They're either independent or dependent. So So let's go ahead and let's solve another system. So this system, I'm actually going to challenge you to pause the video right now, take out a pencil and a piece of paper. Hopefully you've already made a habit, and try to work out this one. So I got as a point 0 and minus 2. So remember, that's always on my, and my next point is 0 and 4. So let's go ahead and draw our line. I hope you were able to get that too. Not close enough. We can live with that, right? Yeah, I don't want to bring up GeoGebra. Number one, I don't want you using it as a tool that helps you do the homework, because what counts is that you can do the problems on the test. The exams are what really count in this class, not the homework. Now over here, notice I did not do the kitty corner zeros. Why? Because our constant term is 0, and that means this linear equation goes through the axis. So already I know when I plug in 0 for x and I solve for y, well, 2 times what number gives me 0? Well, that number is 0. So I've already got 1 point immediately, and it goes through the origin. So let's do another point, and I said let's choose 4 arbitrarily. I kind of looked at the equation to help me out. So let's do it. So I've said x is equal to 4, and we're going to solve for y. It's 2y. So I'm going to divide both sides by 2, and I get 2 is equal to y. So I have 4 and 2. So right there's 4. Let me change it. And right there is 2. So let's draw a line through here. Again, not the best, but visually these two lines seem to be parallel, right? Parallel lines never intersect. So if the lines never intersect, then visually that tells us that there is no solution to this system of linear equations. Well, let's check. So what do we need to do? We need to recall what makes two lines parallel. Our first equation was x minus 2y is equal to 4. And remember, we have y is equal to mx plus b. Two lines are parallel if they have the same slope, and they're distinct if they have a different y-intercept. So what I'm going to do is just put this equation in that form. You already have had practice to do that. So I'm going to divide both sides by minus 2. So I get y is equal to x over 2 minus 2. So that's the same as y is equal to 1/2 x minus 2. So my first slope, m1, is 1/2, and my intercept on my first line is 0 minus 2, which we actually could grab from the graph. And my second line over here, I already know the intercept. It goes through the origin, so the intercept is 0, 0. The x and y intercept are the same, but its equation is x is equal to 2y. So I want this in the form y is equal to mx plus b. So I'm going to put my 2y over here is equal to x, although you shouldn't have to do that. And if you want a b term, you can put plus 0. And I'm going to divide both sides by 2. So this is going to give me y is equal to 1/2 x plus 0. So my second slope is equal to 1/2. So my slopes are equal, and my intercepts are different. So these are two indeed separate lines. Really, we didn't have to do the intercept test, did we? Because we've already plotted it. We know they're two different lines. All we really had to verify is that their slopes are the same. So these are parallel lines. So let's go down and let's kind of state a fact that we just learned. Fact. If two lines are parallel, then remember the context is the system of equations, then the system in here, I want you to think for a second, look at your notes and fill in that blank. If the lines in the system are parallel, then the system of equations is, and I hope you put down inconsistent, because it describes that time when there are no solutions. And remember, when we're talking about solutions, we're talking about ordered pair solutions. Okay, let's do yet one more example. We have 3 really good examples, and I kind of like this because not only it has a visual interpretation, and this is the start of linear algebra, which is literally one of the most important tools in mathematics. In grad school, I would always hang around with those who were getting their PhDs, and we were always talking, and they would say, Kent, take as much linear algebra as you can. Independently, they all would tell me that. So this particular type of algebra is extremely important in mathematics, and I'm really sad that there's only one class in linear algebra offered in Florida. That's the one thing that surprised me about Florida. When I moved here, every other place I've been is linear algebra has been part of the normal curriculum in mathematics. But here, no, there's only one class and it's online, and it doesn't count. I don't think it transfers to UCF. I'm not for sure. Really, some things surprise you. Anyway, it was not that way other places. I'll just leave it at that. Let's copy this over. And unfortunately, it's the one class I would really, really love to teach, because when you're in grad school, you can go all kinds of different directions. Math is very robust, and I chose the pure and computational track. And within the pure track, that means I like to do proofs a lot, and I like to develop computational techniques to solve some mathematical problems. But the pure part was divided down into algebra or analysis, and I chose the algebraic track. Analysis are things like differential equations and calculus, and it's been around since the time of Isaac Newton, but my own personal view is it should be replaced now. On equal footing of that track, on the analysis track, is the algebraic track. that will eventually take place, especially as more people are getting jobs in computers, and to solve many of those computational problems, you have to know linear algebra. My cousin has a master's in computer science, and he's been working for Ancestry for years. Getting paid really, really well, too. And I visited him last summer, and he showed me his math books from when he was taking, getting his degree, and right there amongst them was a book on linear algebra. Of course, he didn't remember any of it. I don't even know if he took it. So let's go ahead and solve this system. Do I have it right? Yeah. So again, our constant value is non-zero. So I can literally use my kitty corner zeros trick. I'm just going to do this really fast. You all should pause and verify that my answers are correct. We're going to do kitty corner zeros for both of them, and remember, I know that's going to work because I have a non-zero constant term in both. So the first one, I'm going to plug 0 in for my x term. So the only thing I'm going to have left is 4y is equal to 10. So I'm going to divide both sides by 4. So y is equal to 10 fourths, which is equal to, this should be reduced, 5 halves. 5 halves, that's equal to 2.5. And that's really the only time I can justify converting a fraction into a decimal is when you have to locate that value on the number line. Then having it in a decimal form is very helpful. And we have to locate that value on the number line here because we're going to plot it. And the next one is going to be 2x plus 4y is equal to 0, but y is 0. So that's going to give me 2x is equal to 10. Divide both sides through by 2. So that gives me x is equal to 10 halves, which is equal to 5. So here are my 2 points. Let's plot them. So 0 and 5 halves. So 5 halves is 2.5. So I'm going to say 3. That 3 is about right there. So I'm going to say about right there is 2.5. So there's this first point. 0. X is 0. Y is 5 halves. So my next point is 5 and 0. And I'm going to say 5 is right there. How's that? And let's go ahead and draw our line. Don't like it. I can live with this one. So this is line 1. We can label it line 1 if we want. That just stands for equation 1. So going back over here to do the next one, I'm going to plug in 0 for my x value. So that's going to give me 2y is equal to 5. So y is equal to 5 halves. Wait! It's the same point. Oh, well, I have a common point. Now let's plug in 0 for my x value. Sorry, 0 for my y value. That gives me x is equal to 5. Exactly the same point. What does that mean? The graph of line 2 is identical to the graph of line 1. In other words, literally, let's do it. If I divide every term in the first equation here by 2, I'm going to get x plus 2y is equal to 5. And that's what I have here. So I know that these two lines are dependent. And hence, the same graph. So here is a challenge question for you. Well, that's not working. Sometimes it has its own little thing. Is the above consistent or consistent or inconsistent. So go back and look at the definitions for consistent and inconsistent systems and tell me what you think. So my guess is some of you want to go with inconsistent, but that's wrong. This is consistent. And this is a case when the solution set remember the solution set is a set of ordered pairs, is infinite. There is an infinite number of ordered pair solutions that solve both of them. And what are those infinite ordered pair solutions? Remember, the two lines are exactly the same, so any point on line 1 is also a point on line 2. So I just drew about 5 or 6 right there, points that are in the solution set. And clearly the entire graph of the line L1 is the graph of all of those points, and that contains an infinite number of points. So let's go back over to the bottom. So this is a really great graph to have. It just kind of visually shows everything together. So here we have two different lines. It's one solution, it's a consistent system, and the equations are independent. The equations are independent because it's a graph of two different lines. Here we have a graph of two parallel lines. The system is inconsistent because no ordered pair solution solves both of them. But the equations are also independent because visually they're two different lines. Here we have one line, actually there's one line drawn on top of another, and there are an infinite number of solutions. Since there's more than one solution, the system is consistent, however the equations are dependent. So all of the stuff we just learned right there is encapsulated in this one drawing. So we're going to find methods to solve a system, and the first method we're going to do is called the substitution method. So literally we're going to solve one of the equations for one of the variables. So you get to choose which equation and which variable, and it doesn't matter. Again, the validity of a mathematical approach cannot depend on a choice you make. We will usually want to use our mind to choose the variable in the equation that will be the easiest. Step 2, we're going to substitute the expression for the variable found in step 1 into the other equation. Find the value of the variable by solving the equation from step 2. Step 4, find the value of the other variable by substituting. All of this is going to make more sense if we just do it, right? So let's just do it. So here are my system of equations. So equation 1, and you can just number them. That's what I always do. It doesn't matter what number you give them. 2x plus 4y is equal to minus 6. My second equation looks kind of weird because there's not a y term there. It's x plus 0y. We have x is equal to 2y minus 5. Excuse me. The first step it says is to solve for a single variable. Well, number 2 is already solved for a single variable. So I'm just going to use number 2. I have x is equal to 2y minus 5. So now I'm going to look, so basically from equation number 2 I've extracted all of the information I can extract. So now I have to jump up here to equation 1. And where I find x, I'm going to write its value as given by equation 2. So just to make sure you see what I'm doing right here, I had 2x plus 4y is equal to minus 6. But here I found out that x was actually equal to 2y minus 5. So this is 2 times x. So I have 2 times, in parentheses, 2y minus 5. And that's just an equation in one variable. And let's go ahead and solve it. So all the information I need right here. So we're going to solve it by normal techniques, by distribution. 2 times 2y is 4y. 2 times minus 5 is minus 10. And then I'm going to add 4y. And then I'm going to get minus 6. So I'm going to collect like terms on the left-hand side. 4y plus 4y is 8y. And now I'm ready to move terms over to the other side. So this gives me 8y is equal to minus 6 plus 10. So 8y is equal to minus 6 plus 10 is 4. So let's go ahead and solve for y. We're going to divide both sides by 8. So y is equal to 4 divided by 8, which you should always reduce to 1/2. So now I know, this is important information, so important I want to star it. Y is equal to 1/2. So if I have an ordered pair solution, my y value is going to be 1/2. So how do I find the x value? Well, if I move up here, I have x is equal to 2y minus 5. Hence, since x is equal to 2y minus 5, and I know the value of y, that means x is equal to 2 times 1/2 minus 5. So x is equal to 1 minus 5. So x is equal to minus 4. So I have exactly one solution, minus 4 and 1/2. Notice this is a non-graphical approach. Indeed, it is an algebraic approach. And it's the only approach that really helps us. Because pretty soon, when we, again back when you're talking about solving systems of tens of thousands of equations, you can't picture that graphically. And if you did, how would you tell a computer to find the solution? Algebraic approaches rule. And that is, if you think about it, the fact that humans developed algebra at all is a great testament to human ingenuity. Now, the book may suggest that you go back and you plug in x is equal to minus 4 and y is equal to 1/2 in both of the equations to see if they work. And indeed, that's a good idea. You probably won't have time to check it on the test. So let's do this next system. It's fractions. So literally what we're going to do is transform these fractions into equivalent equations by finding their LCD and clearing denominators. So this is a really good exercise. So let's just look at the first one, equation 1, and what we're going to do is transform it into equivalent equation. So we want to find the LCD of 6 and 2, and that's going to be equal to 6 itself. Remember, the LCD of two numbers is the largest number is the largest number such that each of these numbers evenly divided. 6 divided by 6 is 1, and 6 divided by 2 is 3. And the LCD of two numbers is always greater than or equal to the largest number. It's equal to the largest of the two if the smaller evenly divides it, and 6 divided by 2 is 3 with remainder 0. So what I'm going to do is I'm going to multiply both sides of this equation by 6. And the answer I get is going to be my new equation 1. And we've not done anything legal because they're the same, they have the exact same solution set. So 6 divided by 6 is 1. 1 times minus x is minus x. 6 divided by 2 is 3, and 3 times plus y is plus 3y. 6 divided by 2 is 3, and 3 times 1 is 3. So this is my new equation number 1. Down here, for the next one, I have to find the LCD of three numbers, 3, 6, and 4. And the answer to that is 12. Why? The LCD is the smallest number that is evenly divisible by every number over here in this list. 12 divided by 3 is 4, 12 divided by 6 is 2, 12 divided by 4 is 3, and that's the smallest such number for which this occurs. So you might want to review how to find the LCD. We will review it in the future, but it's going to be in conjunction with a lot of other things, and I will post a video. The point is we're going to multiply both sides. That's minus 3/4. And when I'm done, I'm going to have a completely different expression for equation 2 that is equivalent. So 12 divided by 3 is 4. 4 times x is 4x. 12 divided by 6 is 2. 2 times minus y is minus 2y. 12 divided by 4 is 3. 3 times minus 3 is minus 9. And that's my new equation 2. And I can just use these two equations instead of the original 2. And that's exactly what I want to do, because I don't want to deal with adding or subtraction, or adding or dealing with fractions. So these are going to be my two equations. So the first thing was to clear the denominators. So now we get to choose the variable in the equation. We have to choose one of the equations, choose a variable, and solve for that variable. We get to choose. It doesn't matter which equation you choose. It doesn't matter which variable. But we want to choose one that makes it easy. So let's choose equation number 1. Because we've almost solved for y. We've almost solved for x. All I have to do is move the 3y over across the equal sign. It becomes minus, and then move the x to the other side. So I get x is equal to 3y minus 3. I'm done. I've solved for x. So now I'm going to come down here, and I'm going to look at 4x minus 2y is equal to minus 9. But x is equal to 3y minus 3. How do I know that? It's literally staring me in the face right here. Then I'm going to go ahead and continue on. Minus 2y is equal to minus 9. So now it's just a matter of solving a linear equation in the variable y. 4 times 3y is 12y. 4 minus 3 is minus 12. Minus 2y is equal to minus 9. So we want to collect like terms. 10y minus 2y is, 12y minus 2y is 10y. And now I'm going to move the minus 12 to the other side, and it becomes plus. So 10y is equal to 12 minus 9, which is equal to 3. So I'm going to divide both sides by 10. So I get y is equal to 3/10. So in my ordered pair solution, I have y is equal to 3/10, but I have to find what's in the x value. So I'm going to go back up here to where I solved for x. I have x is equal to 3y minus 3, and I'm going to plug in the value of y I just discovered. So that's 3 times 3/10 minus 3, and that's equal to 9/10 minus 3. So I've got to subtract those two, and the subtraction just calls for me to find what is 3 with denominator 10. So I multiply 3 times 1. 10 divided by 10 is 1. 3 times 1 is 3. So that's equal to 30/10. So that allows me to do 9/10 minus 30/10, and that's equal to minus 21/10. And what value is that? That's my x value. So my x value is minus 21/10, and that is my solution. So the system has just one solution, and so the system is consistent. And the equations are independent. How do I know that? Because I would have an infinite number of solutions if they were dependent. So let's take a look at another example. So yet we have another way to solve linear systems, and this is our fourth objective. And I actually state it as a theorem. The book does not give it as a theorem, but I like this. So let P and Q and R and S be linear equations in the variables x, y. So if P is equal to Q and R is equal to X, then I can add those two equations together, and I get P plus R is equal to Q plus S. In other words, vertical addition preserves equality too. In other words, I'm literally adding going down. You could also subtract. So remember, subtraction is just another form of addition when you're adding the additive inverse of a number. And that's exactly how we're going to proceed, is we're going to use vertical addition, and what is going to be our whole point is going to be to eliminate a variable. So the first thing we will do is we will rewrite each equation in standard form. Ax plus by is equal to c. So we're not solving for a variable. If necessary, we can transform that equation by one or more by some non-zero number so that the coefficients of a variable are opposites of each other. Opposites mean multiplicative inverses, additive inverses. So that's going to be our second point. Again, this is something you need to see. Add the equations, find the value of one variable by solving the equation from step 3. So let's just do this. You can read through these. You will be required to solve equations both ways on the exam. I did what I did wrong. Okay, here we go. So let's solve this system. So in this case, I don't bother to number the equations at all. I just write them down. I know the top one is equation 1. So there we go. So here's the point. I have to choose. What we need is I have to multiply the top equation by some constant and the bottom equation by some constant so that the coefficient, and we'll choose the x value here, so that the coefficient of the x value is minus the coefficient of the y value. So here's how we're going to do. I'm going to focus on this term right here. So what I'm going to do is I'm going to jump in here, and we're just looking at coefficients. And I'm going to grab the coefficient from down below, which is 4. And I'm going to multiply all of the top equation, both sides, by 4. And now, for the bottom one, I'm going to be doing the same thing for the bottom, but I have to figure out what to multiply it by. So I chose 4, the coefficient of the x variable on the bottom equation, to multiply the top equation by. So for the bottom equation, I'm going to choose the opposite, the additive inverse of the coefficient on x of 3. So that's going to be minus 3. So that's going to give us the following result. 4 times 3x is 12x. 4 times minus 2y is minus 8y. 4 times 10 is 40. Minus 3 times 4x is minus 12x. Minus 3 times minus 3y is plus 9y. And minus 3 times 15 is minus 45. So now I'm going to do the vertical addition principle. Because my whole reason for choosing 4 and minus 3 the way I did is so when I add them together vertically, one of these terms is going to vanish. So 12x minus 12x is 0. Minus 8y plus 9y is just a single y. And 40 minus 45 is minus 5. So I literally just discovered that y is equal to minus 5. So in my ordered pair solutions, I just discovered that y is equal to minus 5. So how do I find out what the value of x is? It doesn't matter. Take any of the equations in any form whatsoever. You can take them in this form or in this form, in the original form, in any equation, and just plug in y is equal to minus 5. So we'll just, it doesn't matter which choice, so I'm over here now. So I'm going to have 3x minus 2 times minus 5 is equal to 10. And I'm going to solve for x. So that gives me 3x plus 10, because minus 2 times minus 5 is equal to 10. So I'm going to subtract 10 from both sides. I get 3x is equal to 0. I divide both sides by 3. 0 divided by 3 is 0. So I found that x is equal to 0, and I'm done. I found the ordered pair solution. So not so bad. Let's just do another example. So let me write down the equations, and then I'll 3x minus 2y is equal to minus 6. 4x plus 5y is equal to minus 8. The only problem, there we go, is I can't change the top bar color in this particular program. I wish I could, because I can hardly see where the top bar is to move it when I need to move it. So again, what I'm going to do is I'm going to multiply both sides of the top equation by some number. And what is that number? It's going to be the coefficient of the x term below it. You don't have to choose the x term, but that's what we're actually happening to choose. We could do this with the y term. And we're going to do the same thing on the bottom system, but I have to choose what number to multiply, so I'm going to choose the negative of the coefficient attached to the x, which is going to be minus 3. And that's going to do it for us. So this is going to give 4 times 3x is 12x. 4 times minus 2y is minus 8y. And 4 times minus 6 is minus 24. Minus 3 times 4x is minus 12x. Minus 3 times 5y is minus 15y. And minus 3 times minus 8 is 24. Oh, how nice of them. So now we're going to do vertical addition. So 12x minus 12x is 0x. I don't even have to bother to write it. Minus 8y minus 15y is minus 23y. Minus 24 plus 24 is equal to 0. So I'm going to divide both sides by minus 23. And 0 divided by minus 23 is equal to 0. So I have one of the values in my ordered pair solution. So I can literally go back to any of my equations and I can use the value of y is equal to 0. So this time we'll use the second equation. It doesn't matter. It works. You can choose any of those 4 equations. 4x plus 5 times 0 is equal to minus 8. So that gives me 4x is equal to minus 8. And I'm going to divide both sides by 4. And that's going to give me x is equal to minus 2. So my ordered pair solution is minus 2 and 0. Okay. So I thought I had another page, but I don't. The next example has to do with applications. The only thing I don't like about this is I want to talk about one thing. What happens if we don't have any solutions, or what happens if we have an infinite number of solutions? So I don't have an example, and I don't have one offhand written down. So I'm just going to write down, so when solving a system of linear equations, not visually, but algebraically. That means by substitution, or elimination. If you discover in the solution that you get, and I'm hoping this is going to be familiar with you, x is equal to x, or y is equal to y, or something like 7 is equal to 7, meaning a is equal to a, then the system is dependent, sorry, not the system is consistent. Why can I not spell today? Consistent. And the equations are dependent. What does this mean visually? Visually, this means parallel lines. an infinite number of solutions. So if, on the other hand, if solving in the same sense as before by substitution or elimination, we get A is equal to B. For example, 5 is equal to 0, where A and B are different numbers. Remember, all the way back when we were solving linear equations, then the system is, and here we're using the exact same word, inconsistent. The equations are independent and graphically or visually we have they're the same line. They're still parallel. They're the same line up here. Visually, two lines are parallel. A line is parallel to itself. So technically, it was correct, but visually, it's just the same line. Visually, down here, we have distinct parallel lines and no solution. Okay, so that's it. Sorry about writing parallel lines there. They technically is saying a line is parallel to itself, but that doesn't help. They're the exact same lines. That's what we mean when we say that they're dependent. Okay, that's it for 4.1.